The last big piece of move semantics is move constructors and move assignment operators. I will go over when and how the compiler implements these things and how you can write a move operation yourself, followed by a bunch of guidelines for how to write well-behaved move operations. To qualify as a move constructor or move assignment operator, the function must be a constructor or assignment operator, obviously, and have a single parameter that is an R-value reference of the class type. The example here shows valid declarations of a move constructor and a move assignment operator. If you don't declare a move constructor, the compiler will kindly declare one for you, but only if you have not declared any of the following: a destructor, a copy constructor, a copy assignment operator, or a move assignment operator. Essentially, the compiler will do the work of creating the move constructor only if it gets to create everything. If it wants to do everything or nothing. Remember this, because it will show up in a guideline later on. Even if the compiler doesn't declare a move constructor for you, you can still request the default implementation of a move constructor using the equals default syntax, just like for many other special member functions. If the move constructor is implicitly declared, or if you explicitly request the default implementation, the compiler will generate a move constructor that move constructs all of the base classes and non-static data members of the object. If any of those sub-objects can't be move constructed, such as if one of them has a private move constructor or a deleted copy constructor and move constructor, then the move constructor will be defined as deleted. The move assignment operator is similar to the move constructor. If you don't declare a move assignment operator, the compiler will declare one for you, but only if you have not declared any of the following: destructor, copy constructor, copy assignment operator, or move constructor. If the move assignment operator is implicitly declared, or if you explicitly requested the default implementation, the compiler will generate a move assignment operator that move assigns all the base classes and non-static data members of the object. If any of those sub-objects can't be move assigned, such as if a data member is a reference type or has a private move assignment operator, then the move assignment operator will be defined as deleted. I have one of the questions: when should I apply the rule of 0 and when the rule of 6? That will be covered a few slides down. Very specifically, that is a guideline. Now for the most important section of this presentation. How do you write a well-behaved move constructor or move assignment operator? The task of a move constructor is to transfer ownership of that object's resources from the source object to the object being constructed. Any parts of the object that are just values that don't represent ownership, such as an int or a double, should just be copied. But anything that is a handle to some external resource, such as a pointer to memory that the object has the responsibility to free at some point, or an open file descriptor or a stood thread object, for those things, the move constructor should transfer ownership so that the newly constructed object owns them and the moved from object no longer owns them. If the sub-object has a move constructor that does the right thing, take advantage of that and call the sub-object's move constructor. If there isn't a correct move constructor available, you will have to transfer ownership of the resource explicitly. How to do that varies depending on what the resource is. Here's an example of a class where the only data members are an int and a string. The move constructor can just call the data members move constructors. We force the use of the sub-object's move constructors by using stood move. For the int, the move constructor is identical to the copy constructor. It just copies the bits. So for the int, we could get away without calling stood move, but I encourage you to call stood move anyway. It better expresses the intent of the code and doesn't cost anything at runtime. The use of stood move for the string is necessary. Without it, the string's copy constructor would be called instead, and that's not what we want here. The constructor that we wrote just calls the move constructors of all the data members. That's the same thing the compiler would generate. So what we have here could be replaced with this, where we ask the compiler to generate the constructor. Here's an example of a class with a pointer to memory that the class owns. The class's destructor, not shown here, frees the memory. If this were real production code, we would use unique pointer instead of a raw pointer, but this is slideware. The raw pointer is a stand-in for any resource whose acquisition and release has to be done explicitly. So how do we write this move constructor? This is a start. We call the pointer's move constructor, so the pointer value is copied to the new object. Like the int, we can leave out the call to std_move since the pointer's copy constructor and move constructor are the same. But we should keep the explicit call to std_move. As written here, the new object is correct. It will free the memory in its destructor like it is supposed to. The problem is the other object's data pointer is still pointing to the same memory. So the other object will also free that memory. That would be a double free, which will likely crash your program. To fix this, other's pointer needs to be set to null. Setting it to null in the body of the constructor works fine. This is a correct move constructor. But there is a better way to do this. By using std_exchange, we can copy the value of the pointer and set other's pointer to null in one expression. std_exchange is very useful when writing move operations. The first argument must be an L-value reference. It's the object whose value needs to change. The second argument is the new value that the first parameter should have. std_exchange returns the old value of the first parameter. It returns it by value, so the return value is an R value. Back to our example so you can see how std_exchange is used. The first argument is the object to be changed, which in this case is the data member of the object being moved from. std_exchange will set other's pointer to null, and it returns the old value of other's pointer, which is used to initialize the data member of the new object. This one line transfers ownership of the memory from one object to the other. When we are done, the new object's destructor will free the memory, and the old object's destructor won't do anything since its pointer is null. But there is one caveat. This move constructor assumes that the data pointer can be null. If there is a class invariant where data can never be null, then the class cannot have a move constructor. In that case, the move constructor needs to be declared as deleted. If data is an owning pointer that can't be null, then there is no way to transfer ownership of the memory from one object to another. Now let's look at the move assignment operator. It's very similar to the move constructor, but there are a couple important differences that need to be mentioned. Like the move constructor, the task of a move assignment operator is to transfer ownership of the object's resources from the source object to the object being assigned to. Any parts of the object that are just values should be copied. But for anything that is a handle to some external resource, the move assignment operator should transfer ownership so that the assigned to object owns them and the moved from object no longer owns them. That's all the same as the move constructor, but there is one important additional task that the move assignment operator has to free any resources that the assigned to object already owns. This task is identical to what the copy assignment operator needs to do, so this part of the operator should be familiar. Oops, wrong way. Let's look at the same two example classes and write move assignment operators for them. First, the class with int and string. The class doesn't own any external resources, so nothing has to be explicitly freed. The string might own some memory, but that will be managed by the string class, not by struct s. All we have to do is call the move assignment operators for each of the data members, which looks like a usual copy assignment operator, except for the use of std_move. Again, this is exactly what the compiler would generate automatically. So we can just declare it as default and let the compiler do all the work. Now for the class that has an owning pointer, where there is an external resource that needs to be transferred. Transferring the pointer value can be done with std exchange, similar to the move constructor. That transfers ownership of the memory successfully, but it leaves out freeing any resources that the assigned to object already owns. To do that, we need to free the memory at the beginning of the function before setting data to its new value. This does everything that I said a move assignment operator needs to do, but there's still one thing missing that I haven't mentioned yet, but that I won't get to for several more slides. So we will leave this example for now and come back to it a little later. Now that you know the basics of writing move operations, some guidelines so you can get better at writing them. The first guideline is that move constructors and move assignment operators should be explicitly no except. The reason behind this is that move operations really should not throw exceptions. Move operations just transfer existing resources from one place to another. Transferring resources should not fail. Allocating new resources can fail, but moving resources around or deallocating resources, as the move assignment operator might do, should always be successful. If you write move operations that want to throw an exception, I suggest stepping back and looking at your class design and whether or not it can properly support move operations. You should always include an explicit no except in declarations of move constructors and move assignment operators, even when asking the compiler to generate one for you via default. And this slide answers a question I got just a minute ago about it. Someone noticed that I marked all the move constructors no except, and this is why. The next guideline, and this is an important one, a moved from object must be left in a valid state. The compiler will call the destructor of the moved from object, so the moved from object absolutely must be in a state where the destructor does the right thing. If practical, you should leave the moved from object in the same state that a default constructed object would be in, but that's an optional part of the guideline. You are welcome to document for your users what value a moved from object will have, but you don't have to. As long as the moved from object is in a valid state, you have satisfied the guideline. This guideline is important enough that it warrants an example. We have a class with a string, and we also cache the length of the string as its own data member. So there is a class invariant that the length data member is always equal to the length of the string. This is a silly design since calculating the length of the string is always trivial to do. But consider this as a proxy for a class where we want to cache some information that is much more expensive to compute. What should this class's move constructor look like? Here's the obvious implementation. Use the move constructor for each of the data members. The class invariant holds for the newly constructed object, since both the string and the length were moved to the new object. But we might have broken the invariant for the moved from object. We know that other.string is a valid string because stdstring's move constructor will leave the moved from string in a valid state. But we don't know what value other.string has. Reasonable implementations of stdstring might leave other.string unchanged or might set it to the empty string. But there's no guarantee that other.length matches the length of other.string. So other might be in an invalid state where its invariant doesn't hold. We need to do something to fix this. One possible fix is to explicitly set other.length to whatever length other.string happens to have after it has been moved from. This is not the best fix because it accesses other.string after it has been moved from, which violates an earlier guideline. We can avoid accessing a moved from object by explicitly clearing other.string. That resets it to a known value. And then we set other.length to be the length of the empty string. This is correct and now satisfies all our guidelines. But we can improve on it some more by using std exchange, which allows us to move the values and reset the values in other to a known state in one shot. This preserves the class invariant in both objects. It has the bonus of setting other to the default constructed state, which is not required, but is a good thing to do. The takeaway from this: if your class has a class invariant, you might have to do extra work in your move operations so that the invariant is maintained in both the source and destination objects. The next guideline: use equals default for your move operations when that will do the right thing. Let the compiler do the work for you, lessening the chance that a typo will introduce a bug. Just be sure to put some thought into whether or not the compiler-generated move operation will do the right thing. Earlier, we had this example, where the move constructor just calls the move constructors of all the subobjects. I said then that using equals default was equivalent. Now I am telling you that it is better. Use equals default when it will do the right thing. This is the most controversial guideline. Some people don't like it, but I stand by it. Make move assignment safe for self-assignment. A move self-assignment should be very rare, especially in well-designed code, but it might happen. And it is up to you as a class designer to make sure a move self-assignment of your class doesn't crash the program. Let's go back to the example from earlier where I left you hanging. A class has a pointer to memory that it owns. We wrote a move assignment operator that correctly frees existing resources and then transfers ownership of resources from one object to the other. But what happens if a user writes a move self-assignment as shown in the code at the bottom? Keep in mind that *this and other are the same object. So when we delete data, that frees the memory owned by the object with no way to get it back. Despite all the work that std exchange does, this line ends up leaving data's value unchanged. So at the end of the assignment operator, data is left pointing to memory that has been deleted. When the class's destructor is run, that same memory will be deleted again, probably resulting in a crash of the program. To avoid this crash, we should insert a self-assignment check at the beginning of the function as shown in blue. This is the same self-assignment check that many copy assignment operators have. Some people worry that the self-assignment check will affect performance. It won't. Don't worry about that. Herb Sutter recently ran some experiments to test this and found that the performance impact of the check is negligible. Just get into the habit of including the self-assignment check in both of your move assignments and copy assignment operators. It will make your code better. The final guideline in this presentation, the rule of 5 or rule of 0. To put it in English, like the core guidelines does, if you declare any one of the destructor, copy constructor, copy assignment operator, move constructor, or move assignment operator, then you should declare all 5 of them. Declaring one of them means providing a definition, declaring it as default, or declaring it as deleted. If the default behavior is correct for all 5 of these functions, then save yourself some work, let the compiler do everything, and don't declare any of them. This is the rule of 0. If you have to declare any of the 5, then there is a good chance that you need to define all 5 of them. You definitely need to think about all 5 of them. Even if you end up using equals default for 1 or 2 of them, do that explicitly to document that you have given it thought. This is the rule of 5. Now, someone in the question asked about the rule of 6. I think the rule of 6 adds the default constructor to this list. So you can follow the rule of 6 if you want to, where you also add a default constructor if that's appropriate for your class. That's fine. But the main point here is define all of them or define none of them. A quick look at some other ways that move semantics are useful. Vector. So how are move semantics useful? Why did Howard Hinnant and many other C++ language designers go through all this effort to get move semantics into C++11? Let's go back to our opening example, where performance was hurt by copies of stdmap being expensive. Move semantics allows us to replace those expensive copies with cheap moves. Here's our code. Remember, there was a copy at the return statement in Build Dictionary and a copy at each of the assignments in Business Logic. Let's see what happens to them when we upgrade to C++11, where stdmap now has a move constructor and a move assignment operator. The copy at the return statement is turned into a move. Remember that a local variable, that is the return value expression, is treated like an R value. So this return uses map's move constructor to create the return value. And we didn't even need to add a call to stdmove. Because the right-hand side of each of the assignment operators is a function return value, which is an R value, these are now move assignments, which transfer the map into the dictionary variable without copying. We have managed to get rid of all the copies without having to change the user code at all. The other big benefit of move semantics is that it makes it possible to have move-only types. Those are the types that can be moved but not copied. This could not be done in C++98. The Standards Committee tried to do that with AutoPointer in the original C++ standard, but they failed. AutoPointer worked correctly if you used it correctly, but it was too easy to misuse it in a way that could result in a program crash or other bad behavior, because the language could not correctly enforce the desired move-only behavior. AutoPointer was deprecated in C++11 and completely removed from the language in C++17. It was replaced in C++11 with unique pointer, which is the quintessential move-only type. Here is some code that tries to copy unique pointers. This results in 3 compiler errors about using a deleted copy constructor or a deleted assignment operator. If we change all the copies to moves by inserting calls to stdmove or using an R value, such as the return value of G, this code compiles without any errors or warnings. This shows that move-only types can be passed by value and returned from functions, as long as the source object is an R value. Ignore the fact that this code uses A after it has been moved from. That was necessary to fit all the code on one slide. Some resources if you want to learn more about move semantics. The most complete resource is Nico's recently published book, C++ Move Semantics, The Complete Guide. I encourage everyone to become familiar with the C++ core guidelines and not just the parts about move semantics. There's a lot of good wisdom in there. Nico has given many talks about move semantics over the last few years as he was writing his book. Earlier in this conference, he gave one that covered some more advanced topics. It makes a good follow-up to this talk. If you think you have figured out move semantics, then I recommend watching Nico's talk from CppCon 3 years ago. That will show you how much you still have left to learn. So our summary, one-slide summary of move semantics. R value references only bind to R values. stdmove turns any expression into an R value and is an indication that you want the object to be moved from. Move constructors and move assignment operators have one R value reference parameter of the class type. Their primary responsibility is to transfer ownership of resources from one object to the other, and they must leave the source object in a valid state. The benefits of move semantics. They result in more efficient code by turning expensive copies into cheap moves, and they enable the possibility of move-only types, which have proven to be very useful. And a review of all our guidelines. No R-value references to const type. No R-value reference as function return type. The next operation after std move is destruction or assignment. Don't std move the return of a local variable. Your move constructors and move assignment operators should be explicitly no except. A moved from object must be left in a valid state. Use equals default and let the compiler do your work whenever possible. Make move assignment safe for self-assignment. And the rule of 5 or rule of 0, which is that if you declare any of the destructor, copy constructor, copy assignment operator, move constructor or move assignment operator, you should explicitly declare all 5 of them. Thank you. So now I will turn to the questions.